So voltage imaging promises kind of the best of both worlds, where you're able to measure the single action potential sort of activity from neurons, and not just a single neuron, but many neurons is the hope. However, it's traditionally been very dim, and we're watching the development of voltage indicators pretty closely with the great and speedy development in the past few years. But still, there are fewer molecules because the voltage indicator is membrane localized, so there's just fewer fluorescent molecules to excite. And the big challenge on our end is it challenged us to develop imaging technology that had that image a lot faster, right? And so the magic number that we heard is that we need to develop an imaging technology that at least goes 1,000 frames a second for a lot of the dream experiments that people want to do to measure single action potential activity. And so I'm proud to announce that we created a module that achieves this, and we call it the OptoVolt. And it's an add-on to the Ultima 2P+, that gives you kilohertz imaging rates, not only for voltage imaging, but for imaging neurotransmitters that have fast dynamics as well. Like I mentioned, it adds on to the resonant scanner of the 2P+. It's compatible with the Neuralite 3D Ultra for combined voltage imaging and holographic photostimulation for optogenetics. And in order to do this, we needed to redo our digitizers in order to maximize signal to noise. And like many of our developments, we did this in collaboration with our academic partners. And in this case, it's Boston University. And the effect is that it gives you this kilohertz scanning by accelerating our traditional rest or scan from resonant mode, where the time it used to take for scanning a single beam in your sample, now we scan 16 beams in the same time. And it's kind of thanks to, let me go back, this micro lens array, where the multiplication factor is based on the number of micro lenses that you scan across. In this case, it's 16, which gives us a 16x increase in speed. We do have a mode in our system that allows for a bigger field of view if you don't need to go as fast. And so for around 500 hertz, you can get double the field of view in each axis. And it's software selectable, so we could switch between the larger field of view mode or the kind of high speed mode. You can also switch between that and the traditional modes that are on our system for imaging tissue or calcium imaging. And since you generate images, the workflows are pretty much the same as if you were imaging calcium, where you're able to send the data through the same pipelines for analysis, extract your traces, identify your cells. And so again, in summary, the beam comes up to our system and it gets piped into this OptoVolt module, which scans across these micro lenses before getting rescanned back into the sample. And this was a great development that allows us to add it on to our system. It utilizes the resonant scanner that's currently in our system that we have expertise with, and now we're able to offer it as an add-on without buying a new system if people want to pursue voltage imaging. And so in the past, voltage imaging was done in our systems already, but with a much smaller field of view. And so this was the type of imaging that was done where you can reduce the field of view and get voltage imaging of few cells at really high signal to noise, which is shown by the traces below. But now with the OptoVolt, we're able to increase the field of view and retain the speed. And so this is data from Michael Hauser's lab. He's using voltage indicator Force 1S that was recently debuted at SFN 2025. And so here he's imaging at the 8x mode, which allows us to get a larger field of view. And so this is using a 16x objective, 300 micron by 300 micron field of view. And he's able to send the data through Suite 2P to do the cell identification and trace extraction. And so he's able to find 513 regions of interest here. And he was able to show that he's able to image at a kilohertz as well with a smaller field of view, and also identify many ROIs. The nice thing that the imaging gives you is that it gives you ability to look at when does a localized activity happen, when does activity happen for this cell given its neighbor cell and in relation to the neighbor cell, and you get to see the signal propagation throughout the entire field of view because you have this image at maybe at 565 hertz or kilohertz. And so the dream experiment, of course, is to combine this with optogenetics, where you're not only looking at cells with your voltage indicator, maybe a postsynaptic cell, but you're able to also activate the corresponding presynaptic cell as its partner and do this functional mapping experiment across the brain, right? And so you can change your field of view and repeat this and hopefully get a functional map of how neurons are connected throughout the region of interest.